Okay, everybody, Guido here. Today we're going to talk about binomial distributions and how they play a part in simplifying your probability calculations. So, first of all, what are the goals here? Recognizing conditions that give rise to a binomial distribution, making connections among the table of values, the histogram, and algebraic representations of a binomial probability distribution, and to solve some problems involving binomial probability distributions. Okay, so first off, what are characteristics that allow you to determine that you are considering an event that involves a binomial probability distribution? First of all, there are independent trials. Key words that you'll hear are words like replacement and repetition in the event. It involves a two outcome scenario where there is success or failure that is being counted. Therefore, the discrete random variable x is the number of successes. So, random variable x is the number of successes in a given number of identical independent trials, variable n. And finally, the probability of success, lowercase p, or the probability of failure, lowercase q, in any individual trial remains constant. It does not change with each trial. For example, if you draw diamonds from a deck of cards, the probability is 13 out of 52. And if that card is replaced back into the deck, the next trial of drawing a card, drawing diamonds, the probability of drawing diamonds remains 13 out of 52. So the probability of drawing the diamonds has not changed. And if the event that you're trying to solve for is the number of diamonds drawn from a deck of cards in a particular given number of trials, then your probability of success is the number of diamonds that are drawn, and that doesn't change with each trial because of the replacement. Therefore, it follows the characteristics of a binomial probability. And as such, there is a formula that reduces your probability work from earlier lessons on probability to a calculation as follows. The probability of discrete random variable x is the combination of n trials, choose x successes, multiplied by the probability of success on one given trial to the exponent of the number of successes, multiplied by Q, which is the probability of failure on any given trial, raised to the exponent of n trials minus x successes. And the expectation for a binomial distribution can be also simplified and become more efficient. It simply becomes the number of trials multiplied by the probability of success on a given trial versus the standard process, which would have been to do the third column in your table and multiply each x value by p at x, add them all up, and that sum of the third column, which is the sum of x times p at x, becomes your expectation value. So this could be a very involved task with many possible rows in your table that has to be calculated. This whole process is simplified simply by multiplying n times p if it matches the characteristics of a binomial distribution probability. Okay, so let's consider a scenario here. This is example 2, your turn. If you're using the McGraw-Hill Nelson textbook, it's page 165, and it is as follows. A family has 6 children. Consider a probability distribution for the number of girls in the family, and then answer the following questions. So A, identify the discrete random variable. That is the number of occurrences of a girl in this family. Calculate the probability distribution. And then C, verify the sum of the probabilities is 1. Part D, graph the probability distribution, compare the shape of the histogram. And finally, E, calculate the expectation and interpret its meaning. Okay, so let's continue. Part B, complete the probability distribution table for the number of girls in a family of 6 children. So, discrete random variable X is the number of girls, variable X. If it's a 6-child family, there could be as few as 0 girls and as many as 6 girls. And then we take the analysis of the criteria for binomial probability. Are these independent trials? Is the probability of having a girl on one occurrence, which is 50%, does that remain the same with each next child that is born? So, for example, the first child, is there a 50% chance of it being a girl? The second child, is there a 50% chance of it being a girl, etc.? Are these independent trials? The answer is yes. Is there a 2 outcome scenario? Yes, it could be a girl or it cannot be a girl. Is the probability of success 50% remain constant with each new child that is being born into this family of 6? The answer is yes. Therefore, we have satisfied the criteria for a binomial probability distribution. And if we consider the first case, 0 girls, the calculation becomes the combination of 6 choose 0 times probability of success to the exponent 0 times the probability of failure to the exponent 6. Let's consider 1 girl being born. That becomes a calculation of 6 combination 1 times 0.5 to the exponent 1 times 0.5 to the exponent 5, and so on until we've exhausted this scenario of 0 minimum to a maximum of 6 girls in a family of 6 children, and the resulting calculations and the resulting third column, which we will use later to calculate the expectation. So now let's verify that the sum of the probabilities is 1. If we add up this second column, the probability column, you'll see that you'll end up with 1.00, which is 100%. And because the sum of the probabilities is 100%, we have a complete distribution table. The table is complete and the distribution is complete. Therefore, we can move on to the next part of graphing the histogram. And I use the graphing calculator here. You could do this by hand. The pencil paper, the vertical column, the y-axis would be your probabilities. And looking at the table here, you could see that the least probability is 1.5%. The greatest probability looks like it's 31.25%. So if you make your table go up by 0.1s or 10%, you have 10, 20, 30, and approximately 40%. And you could draw the height of your bars for each case. The first bar is the 0 successes, then 1 success, then 2 successes, then 3, then 4, then 5, then 6 successes. And we have a histogram that appears to be peaking in the middle. It's slightly off center. The peak is slightly to the right. Notice from the table that we have 7 situations, 7 cases, and the 1, 2, and then 1, 2 off the back. And then we have 1, 2, and 3. And actually, looking at the probabilities, it is symmetrical. The peak is at 3, and then it symmetrically decreases left and right of the peak. So at first, it appears to be slightly skewed left, but it's actually perfectly symmetrical, which makes this a perfect bell-shaped curve. Another name for this is a normal distribution. Okay, so let's move on to part E and the expectation. So we could use the standard process and multiply x times p at x, which is the third column in our table, for each case, each row, and then add them up, and we'll get an expectation of 3. We could also use the more efficient process for expectation, since this is binomial, and given that it's binomial, the expectation will simply equal n times p. And in this case, n is the total number of trials. And since it's a 6-child family, that means the total number of trials is 6. And the probability of success on any given trial, which is constant, is 50% likely to have a girl. So 0.5. And because this already satisfies the binomial probability, n times p could be our more efficient process for expectation. And as you can see, 6 times 0.5 is going to equal 3. So in either case, in either method, the standard process for expectation or the binomial process for expectation both lead to an answer of 3. And what does this answer of 3 mean? What's the interpretation? That the average outcome for a family of 6 children in the long run will be 3 girls. So this is the expected average in the long run, the theoretical average of what may occur in a family of 6 children. There's no guarantee. This is theoretical. And thank you for listening to this lesson on binomial probability with this given example of the number of girls in a family of 6 children. Thank you and have a great day.